So today we will speak about groups. So why the notion of group is relevant for physics? Well, it is related to a naive idea of symmetry. What is in this sense, a very vague sense, is an invertible map on a set that leaves unchanged certain of its properties. Let's say, for example, you have a sphere. You can rotate it around any axis and leave the support invariant. So rotations leave the support of the sphere invariant. So there is what is called symmetry under rotation. It is surprising that the first example of a conscious search for symmetry by man was more than 1 million years ago. I want just to show you this because for me it was always surprising. Okay, in nature you easily find the symmetry which is symmetry with respect to an axis, so bilateral symmetry. But at some point the prehistoric man start to chop the stones in such a way that they were respected, of course, approximately, not only the symmetry with respect to an axis, but also to pi rotation, which is not so common in nature anymore. And there is no utilitarian reason for that. So it must be kind of natural search for symmetry. So a mathematical implementation of the idea of symmetry is precisely the group. What is a group? A group, let's call G, is a set with a law of composition of its elements. Let's call, so typically a group will be denoted by G and the composition law, but most of the time the composition law will not be written explicitly, under which it's closed. So you take two elements of your set and you act on with the composition law, you just get again an element of the set, satisfying the following properties for every G, G1, G2, G3 in G: associativity. So if you first act G1, G2 composed with G3, or you first do G2, G3, and then act on G1, you get the same. So this is in fact exactly what you expect from the composition of masks that leaves invariant some property. So this is related to the naive idea of symmetry. Second, existence of a neutral element let's call E, such that E composed with G is equal to G composed with E is equal to G. And of course, this is just an identity map in this logic of symmetry. And 3, existence of inverse. So G minus 1, such that G minus 1 composed G is equal to G composed G minus 1 is equal to E. And this is the idea of invertible map. So if you have a group, you can define what is a subgroup. A subgroup, let's say H, is a subgroup of G. So, of course, H is a subset of G. If H is a group under the composition law. Of G. So there are, of course, in many examples. There are, for example, groups which are associated to symmetry of space. So, for example, Euclidean space, let's say, which are Roto translation, or to Minkowski space-time, which is a Poincaré group. And also, for example, set of numbers. R with addition is a group, but for example, not the natural number with addition because there is no inverse. Can I move the sheet of paper?
Yeah, it's okay.
Okay. Then we have groups of n times n invertible matrices. For example, R, which is real and satisfy R transpose R equal to the identity, R describe the ON group. If you add the condition that the determinant is 1, you get the SO1 group. If you take a U which is complex and you dagger U equal to 1, you get the UN group plus the determinant of U equal to 1, you get SUN. And generalizing this, thinking that this is R transverse is some identity R equal to 1. So this you can think as the Euclidean metric in Cartesian coordinate. You replace this by the Minkowski metric. Well, then, of course, you have that lambda transpose eta lambda equal to eta is a Lorentz group. If you are in 4 dimensions, it's 013. If you add the condition that the determinant of lambda is equal to 1, you get S013 and so on. We say that the two groups G1 and G2 are isomorphic if there exists a map F from G1 to G2, which is invertible and preserving the group properties. So an isomorphism of a group G on itself is called automorphism, and the set of automorphism of G is itself a group with the law of composition of maps. And that this called usually is called denoted out of G. Another notion which is relevant for group is the presentation of a group, which typically is written as something like SR. So the idea is that you identify a set of elements, let's call S in G, call it generators, such that all the other elements are obtained from them by composition and inversion. And so S is the one element, one of the two pieces of this notation, and a set of relations, let's call R, identifying when these products give the same element. Let me give an explicit example, which maybe is familiar to you.
Could you please show the last page again?
Ah, sorry. Okay, sometimes my writing is not very nice, but
Okay, thanks.
Can I move? So let me give an example, probably familiar to everybody, but maybe not the fact that it's a presentation. So it's a permutation group of n elements, which is denoted in many ways. One possible way is Sn. And let's consider sigma I should be the exchange of the i's with the i's plus one element. Let's denote in symbolic notation, like I have an I plus one, and just exchange I and I plus one, the position of I and I plus one. Well, then Sn has the following presentation, is the set of all the exchanges at sigma I from 1 to n minus 1, such that, so this is the generators, such that they satisfy the following property: sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. Then sigma j is equal to sigma I if I minus j is greater or equal to 2. And finally, sigma I square is equal to the identity of the group. So let me just make a drawing for this. So you have your I plus 1, and you exchange, and you have three positions. So you exchange I and I plus 1. So and then you have sigma I plus 1, which exchange I plus 2. So either you first exchange these two and you leave this invariant, you exchange these two and leave but this invariant, and then you exchange again these two but leave this invariant, is equal to instead you leave first this invariant, and then you exchange this and this. Then you exchange this and this, leave this invariant, and then you exchange this and this and this invariant. So I plus 1, I plus 2. So the identity of these two operations gives you this relation that I wrote there. There is one very interesting group, which is the fundamental homotopy group. Is another example. It needs some time, but I think it's useful. That's called pi1. So let me first introduce the idea of homotopy. What is the homotopy? Let's suppose you have M and N, they are topological spaces. And you have two maps from M to N, let's call F0 and F1. And you say that F0 and F1 are homotopic if there exists a function f from 0, 1 times M to N. So that usually I denote by T, maybe this element in the interval 0, 1 to N, such that for every P point in M, this function evaluated at 0, P is equal to F0 of P, and F of 1 and P is equal to F1 of P. And you have a continuous function which has this property. So now let's introduce another concept that I needed to define the homotopy of group. What is a loop based at a point P in a topological space M? So let's consider a curve gamma which is map from 0, 1 to M. And if it is a loop, it also satisfies gamma of 0 equal to gamma of 1. And if it is based on P, this must be equal to P, which is the base point. Let me just maybe make a drawing. Suppose you have your topological space, something like this. Then your gamma, you pick a point P, which you are interested, and the gamma will describe some oriented curve here. Well, then there is a group which is pi1 of M and P, which is given by the equivalence classes of homotopic loops in M with base point P with the composition of loops given by a kind of normalized composition of maps. Let me show, maybe it's easier to see in drawing that in Word. Can I move the paper?
Yes, from my side.
Okay. Let's suppose you consider, for example, R2 minus some disk. And maybe more than one disk. Let's suppose you have two disks. Well, then you have, for example, a map, which you pick a point P in here, and you go around by some curve. That's called gamma 1. So this is one possibility. We have another curve same situation. So you have omitted from R2 these two disks, same point P, and now you do a curve like gamma 2. Well, then gamma 1 composed gamma 2 is given by same situation. You have omitted these two disks. Is given by going from P along gamma 1 and then back to P again with gamma 2. So it is interesting to notice that suppose you have R2 minus only one disk, for example. Then, for example, orientation of the curve is relevant. So this curve is not homotopic to the same curve in the opposite, with the opposite orientation. However, it is homotopic if you deform it also in very strange way. You can deform like this. It doesn't matter. It's still homotopic because you can move continuously. So it turns out that if your topological space M is connected, the fundamental group with base point P is independent on the base point, and so it is just, you just know it about pi 1 of M, independent of P. And you can really easily check. I mean, suppose you have simply R2 minus only one, which is very easy case. You consider the loops, and then you can associate to homotopics class that how many turns with orientations. So 1 or 2 or okay, which imply that pi 1 of R2, for example, minus the origin, since it corresponds to the turn with orientation, these are just labeled by integers, so it's isomorphic to that. Okay, now the next concept that I want to introduce is the action of a group G on a set or a manifold. Let's say a set X or a manifold M. Okay. You can have, it is, what is this action? It is a map from the Cartesian product G times X, let's say X, to X in general, or G times M into M, which sends a point G, which belongs to G, and a point X, which belongs to the space X, topological space X, of course, to phi of G and X, which we denote in very simple way by G of times X, such that if you compose first G1X and then G2, so you act on this point with G2 after you act on it on G1, it is the same as acting with the composed G1 times G2 on X. Now the orbit of a point X, which belongs to a big X, is the set of Gx such that G belongs to G. And instead, the isotropy group of a point X in X is the set of the G such that Gx, so when you move G acting on X, you get back to X. And sometimes it is denoted by G with a little X below. And finally, phi is called transitive if there exists only one orbit to the action. Let me, for example, let's say, an example that I will repeat later on. Suppose you have two spheres. You have point on the two sphere. Of course, you can act on this by rotation. So you act on S2 by rotation, which maybe is SO, for example, 2, if it is rotation just around one axis, or SO3 if you act in all corresponding to every axis, then it's SO3 according to our definition. Is it fine? Can I move the paper? Okay. Then following this, you have the notion of quotient space. What is a quotient space? Suppose that you have a group H, which acts on your topological space X, and we declare 2 points of X equivalent if they are in the same orbit. So the set of orbits, so the set of these equivalent classes is called quotient space and denoted by X divided by the action of the group H. It can be that X can be itself a group. Let's see, G. And H, a subgroup of G. Okay, probably I forgot to say that if G acts like in this way, it's called a right action. Sorry, left action. So this is left action. Sorry, this is a left action. And instead you act on this side, it's called a right action. Okay, I forgot to say. Okay, so X can be itself a group and H a subgroup of H, of G. Let me give an example. Suppose that you take as group G the real numbers and the subgroup H the integer numbers, which act on G, so on R, by translation. Then what you do, you have your R, you have your integers, n plus 1, and so on, and you identify this with this, and so on. You identify this with this by translation. What happens is that since you repeat it any times, you take is equivalent to take a single interval with identification of the initial and final point. So according to this rule, we denote this identification with R, quotient by Z. But because it's identification, we see this is equivalent to a circle. If you think a little bit, a circle is equivalent to a group U1. But this, so it can be that you have your action of a group on a group, and the quotient space is a group itself, but it doesn't happen always. There is a nice theorem which tells you that if G acts transitively, so having one orbit on X, then G, the quotient space G over Gx is isomorphic to X itself. Let me give an example. Suppose you take a two-sphere and you act on it by rotation around any axis. You can bring any point P using rotation to any other point of the sphere. So SO3 acts transitively on our X, which is in this case S2. However, if you take an isotropy point, SO3 of X, you immediately realize that the only rotation which leaves invariant the one point P is the one which corresponds to rotation through the axis going through P. And so you immediately find by the above theorem that SO3 quotient by SO2 is isomorphic to S2, but S2 is not a group. So it's not always true that starting from a group, you're a subgroup, take the quotient, you get the group. Why it fails? Because you find that the sufficient condition for G over H be a group is intuitive, is that if you act with H and G on the left and on the right, you get the same result as equivalence classes. So these are the equivalence classes. For example, GH, H in H, and so on. So this is one. With the composition law, G1H times G2H equal Q1G2H. And now it is clear why you want this property here. Intuitively, from going from here to here, you just move this, which means that you want to, instead, H times G2 should be equal to G2 times H. And then it's somewhat natural that you get this result. Can I move? Can I move the note?
Yeah.
Okay.
Yes.
It's fine.
Okay. So let's turn to operation that you can make on a group, on two groups, sorry, operation on groups. So one operation is the obvious one, is the direct product. I don't comment too much on this. It's G1 times G2 is the set of couples G1, G2 with natural compositions. So for example, the couple G1, G2 composed with G prime 1, G prime 2 equal to G1, G prime 1, C2, G prime 2, and so on. More complicated is semi-direct product. Now I define, looks very complicated, but actually in physics you already know this. Now, suppose you have N and H, which are groups, and you have a map phi, which sends H into the automorphism, so the map of N into itself, which sends so an element of the group H into some N, which is mapped by some map phi of H, which depend on H. Well, then the semi-direct product of N with H, which it is denoted in this strange way, is the set of couples N and H, but with a very strange composition. NH1 and N1H1 composed N2H2 is equal to N1. Now compose phi of H1 and of N2. Remember that phi is, so this is still an element of N, so it's naturally composed with N, but it's not the natural one, not just N2. And instead the second is just what you expect, H1, H2. And the inverse N of H inverse is by definition of phi of H to the minus 1 of N to the minus 1 times H. The second is N. So this is semi-direct product. It's not new to physicists. Why? Because rotor translation are precisely in n-dimensional Euclidean space, are precisely the semi-direct product of Rn with SON. So an element of Rn, let's denote by A, an element of SON you denote by R, and let's consider the transformation. You first start with a point, which is the one coordinate in your space, so an element of your space. Of course, everybody knows that if you act with A2, R2, you get R2x plus A2. You act again by A1, R1, you get R1 acting on R2 of x plus A2 plus A1. So in the end, this is R1, R2 of x plus R1, A2 plus A1. So it recognizes that A1, R1 composed with A2, R2 is equal to R1, H2 plus A1 times, and the second couple is R1, R2. So it's just semi-direct product with the rule that phi A of R is just RA. And the same is similar is the Poincaré group in, let's say, 1n, where this is time and this is space dimensions. Again, this is the semi-direct product of R1n in the Minkowski translation times O1n. This is what is called the Poincaré group, P, Poincaré. Okay? Can I move?
Yep.
Okay, so now let's turn to another concept.
I'm sorry. The
Please?
definition of the semi-direct product depends on the map phi that we choose, doesn't it?
Yes, it depends on the you need to specify what is the map phi. So sometimes, in fact, you just put the phi here to denote the map, but most of the time you don't. For example, so okay, to be precise, you should write the 5, yes. So the next notion that I want to introduce is the notion of representation of a group. Let me motivate. We have already seen that we can represent the group, for example, of symmetries of space-time or Euclidean space or space-time. With matrices acting on vectors, which are the X, which is composed to Cartesian coordinates. And in quantum mechanics, any map on ray vectors. Remember that the ray vector is a way of representing pure state in quantum mechanics. Of the Hilbert space.
I'm not familiar with the concept of ray vectors.
Of ray vector, it's given a vector, you multiply by any complex number which is different from 0, and you consider this set as an element is called a ray vector. So it's if you want the one-dimensional space which is parallel to one vector except for the 0 which is not included. If you think a little bit, any state in quantum mechanics can be represented by a ray vector because somehow the modulus of the vector is irrelevant. It's only what is relevant in quantum mechanics only somehow the direction of the vector in the complex space. Okay. So now in quantum mechanics, any map on ray vectors of the Hilbert space H that preserves the transition probabilities, which is the physics. Physics always described in terms of transition probability. So it is a map on ray vectors, so on pure states, if you want, that preserve transition probability. So according to our definition, is a symmetry because it preserves some property of a set. Actually, many times this symmetry is called in quantum system a physical symmetry. To distinguish maybe from the dynamical symmetry, in which you require that also the Hamiltonian is left invariant. So we see that both classically and quantum mechanically, we have the idea that we want to represent symmetries and so groups in terms of matrices or more generally linear operators. To represent groups by matrices or by linear operators. That's what happens when you discuss the quantum mechanics case that maybe I just flash on later on, acting on a vector space. Okay, in the classical case, just a space of coordinates, maybe, or in this case, it's just a very sophisticated object, which is a Hilbert space. But anyway, in both cases, it's a vector space. And so this suggests that there is a very important definition. Let G be a group, be a vector space. The automorphism of B is a space of linear invertible operators on V, so for finest dimension is just matrices, then a map D from the group to the automorphism of V is called sometimes you add the word linear representation of G in V, which is called the representation space. If the following holds, this map is such that D of E is equal to the vector 1, and D of the one you respect, D of G1, G2 is equal to D of G1, D of G2 as operator acting on V. So the dimension of this vector space is called the dimension of this representation. Can I move?
Yes.
Okay. So there are special cases in which are very relevant for physics of representation. If V is a Hilbert space, and D of G, so the operator, let me denote by U of G, is a unitary operator, the representation is called unitary. The more sophisticated, if U hat is the set of operator U prime differing from U by a phase, and you construct a representation using these, which are unitary ray vector, U of G provides what is called a unitary projective representation of G. And why this is important? Because Wigner theorem, now we connect with our definition of physical symmetry, states, very non-trivial and very interesting and not easy theorem, states that a physical symmetry in quantum mechanics is represented on pure state by a unitary or anti-unitary, but I don't want to insist on this, anti-unitary projective representation. So this is the most general thing that happens to describe a symmetry in quantum, physical symmetry in quantum mechanics. It's not really a unitary representation of your physical symmetry, it's a projective unitary representation. Then maybe it's a unitary, but you're not sure a priori. Okay, so when you have introduced the concept of representations, we can introduce the concept of equivalence when two representations are equivalent. So two representations, let's call D1 and D2 of G, are called equivalent if there exists an operator A on V invertible, an operator A from V1 sorry, A from V1 to V2 invertible, such that A of D1 of G is equal to, so D1 of G acts on V1, A acts map V1 into V2, so is equal to, first you take A, you map V1 into V2, and then you act with D2 of G. If this property is all, but A is not invertible, so you still find a relation like this. But now A is not invertible, A is called, or you do not require to be invertible, it's called an intertwiner. Is not required invertible, and it's called an intertwiner. So a natural question is that given representation D and the space, vector space V, a natural question is if D of G, so the representation of G leaves the vector space invariant. For example, suppose you have the two-dimensional space R2, which is embedded in R3. Then, of course, any rotation of this kind leaves R2 invariant. Instead, if you perform a rotation around an axis which is not the vertical axis, okay, this is not invariant. So then you get the following notion: a representation D of G on V is called irreducible if the only invariant subspaces are B, and of course the one which is always invariant is 0. So except for the trivial case of 0, a representation is called irreducible if it has its own invariant subspace B itself. Can I move?
I would have a question about,
Yes.
So in the definition of projective representation, it seems like you didn't give a prescription of you don't have to give a prescription of phase in order to have it.
U1,
So
UG2 equal to U hat G1, G2. Is that what you want?
okay, no, but about the phase, because
Any phase.
any
To the
phase.
I alpha, any phase. You say that you have, U hat is the set of all the unitaries which differs by U, just by a phase.
Okay. Okay, because I think I saw it some other times in which it seemed like you start from a linear representation, and then you from the linear representation you construct a projective representation giving a prescription of the phase that you get for every multiplication. But somehow there was like
I mean,
y alpha of G1, G2, something like that.
yes, that is equivalent. If you think a little bit, this is equivalent. You can pick a representative for any of these equivalence classes, and then you construct a situation in which for the representatives, you correspond to this rule that I gave here. It's equivalent. If you are careful to pick the phases, this is equivalent. Yes. But I think this is, to me, is more natural, because in quantum mechanics, the pure state are ray vectors, and so on the ray vectors in which you do not specify the modulus, it's natural that acts not a unitary operator, but a projective representation, because this don't know about the phase. You know, I mean, you can change the phase of a state in quantum mechanics without changing anything. So it's very natural that the symmetry are represented not strictly by unitary, but unitary modulo phases. That's why. Okay.
Yes, thanks.
Can you precisely define what a projective representation is, please? Because for me, it's not exactly clear from your explanation.
Okay, you have a set of when you have a set of unitary operator differing just by a phase, and you impose this law. So you can pick, if you want, a representative. So you can take one representative, U of G1. So you pick one representative, U of G2. But now you do not get G1, G2, but you have also a phase which depend on G1 and G2.
Okay.
Respecting this property. Okay.
Okay. And then you don't care about this phase, because I was just familiar with the fact that you don't care about the phases in the vector space.
And yeah,
not
exactly. And here it's the same. The
Okay.
symmetry is such. In many cases, you can replace a unitary symmetry by a projective symmetry by unitary symmetry, but not always. And that's precisely the case of rotations, in which you find that rotation represented not by unitary operator or representing rotations, but if you are familiar with SU2.
Yes.
And so that's the origin of this. Okay. Let me give an example of rotation which are irreducible and not irreducible representation. Suppose you consider a representation of rotation around an axis, and you take a vector space R2, and you take matrices of cosine theta minus sine theta, cosine theta. But this is irreducible. This, of course, you can. There is only one space, and you just map the. But suppose you do it on R3. Now you have to cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, and 1. Well, this still rotate the plane in itself, but this is not the entire R2 that is unchanged by this action of the group, because also any of these subspaces is left invariant by the group. So this is not irreducible. So this example suggests that if you have a representation D1 and then a representation on a vector space V1 and a representation D2 on a vector space V2, you just compose them in the case of matrices by D0 block diagonal, and this still is a representation. On V1 target sum V2, but not irreducible. Because of course, because of living. So that you can in a sense think irreducible representation as a kind of building block to construct the other representation. Via direct sum. So the basic theorem for irreducible representation is the so-called Schur lemma. There are two. Suppose you have D1 and D2, they are irreducible. And A is an intertwiner between them. Then the Schur states that either A is equal to 0, well, that is always possible, or A is invertible. But if it is invertible, then we know that D1 is equivalent to D2. So if you have two irreducible representation of a group G, and there is an intertwiner, well, then the two representations are equivalent. And the second Schur lemma states that if V is complex, it doesn't work for real. And D irreducible. And A is an intertwiner of D, the representation with itself, which of course it can be, then A is a multiple of the identity. So we already know something very, that A, there is some alpha which belongs to C, such that A is necessarily a multiple of the identity. So this is a very powerful lemma. So if D is reducible and you have an intertwiner with itself, fine. This is just a phrase. Can I move? It's fine?
Yeah.
Okay, let's introduce the last big notion, which is the notion of a Lie group. Suppose now, up to now, we do not require anything on G, it was a set, but if G is also a manifold, a smooth manifold. But smooth in this case, the real definition would be really analytic, but it doesn't matter. There is a theorem that as soon as it is C1 is analytic, it doesn't matter for the group. But anyway, is a smooth manifold of dimension n. Notice that now we can introduce the concept of dimensions of a group. That and the group operations are also analytic. So all the structure is analytic. Then G is called a Lie group. And it can be shown very easily that all the groups of matrices defined before are Lie groups. It is not immediately which is the dimension of the group, but they are all Lie groups. Why Lie groups are very important? And because they have another property which in general groups do not have. So there's a crucial property. Since G is a manifold, they have, of course, a tangent space. In particular, you have a tangent space to the identity. Okay, this is all time and space. Of course, is a vector space. But the point is that the group structure provides an additional structure. So an additional operation turning T of G into an algebra. And for matrix Lie group, the only one I speak about, so group of Lie groups which are made of matrices, is defined as follows. You can give two curves in G through the identity. So you have your G, now G is a manifold, okay, very good. So you pick your identity, E, which is in G, and you have two curves. Two curves means that you have one curve, maybe that's called A of T, and the second curve, which is called, let's say, okay, B of T. And of course, we know that any curve to any curve is associated a vector, okay? So it will be a vector here and a vector here. We have discussed this last time. It's the vector, which is a differential operator, which is determined by the curve. And so you have given two curves, what that's called, so A of T and B of T. They, of course, they have associated vector, tangent vector. Let me call A and B. And now you consider the curve, which is given by the following. C of T is equal to A square root of T times B square root of T. Now use the matrix multiplication. Times e to the minus 1 square root of T and B square root minus 1 square root of T. And now the point is that since the dependence of T is analytic, that's why we need a Lie group. We can expand in T. And then you take the leading term. It turns out that the leading term out of this is just AB minus BA. Okay, so what you call the commutator of A and B. And so, but here you have a vector C. So C is the commutator of A and B. And so now you have defined a new operation on T of G, which is this, which is called a Lie bracket on T E of G. We turn it in what you call a Lie algebra. Now the Lie algebra I denote by Lie of G in this way, Lie G, because I should use a script for the G, which is I cannot do. So what are the properties of this Lie algebra? Well, the one you expect. Oh, sorry. Is it fine to move? Can I move?
Yes, go ahead.
Yeah. So what are the properties which characterize the Lie algebra? Well, of course, the one you get from the commutator. One is antisymmetry. So the commutator or the Lie bracket of A and B is equal to minus the commutator of the Lie brackets of B and A and the Jacobi identity. Which is A, Lie bracket B, Lie bracket C is equal to, and now it's cyclic, B, C, A plus C, A, B is equal to 0. So these are the Crisemans. So TEG with together with is what is called LG. So you see now, because first of all, okay, you have your tangent space, it is a manifold, but you have also the group property, and the group property have this combining with analyticity, give you this additional structure on the tangent vector. But now, since Lig is a vector space, it has a basis. Let's call E alpha, and of course, since it has a dimension, the manifold of dimension n, of course, let's go up to the dimension of G. And the Lie bracket between elements of the basis can again be expressed in terms of combination of the basis. So there must exist some numbers F, alpha, beta, and gamma called structure constant of the Lie algebra, such that the commutator of the Lie algebra, the Lie bracket of two elements of your basis, of course, can be written as alpha, beta, gamma, E gamma. That's it. Now, notice that we discussed the Lie algebra as a tangent space to the Lie group, and so from the definition, if A of t is a curve, and we say that this is an element of the Lie algebra, from this equation, one gets the suggestion that this curve I can write as et of A, exponential, because if we differentiate this, just I get exactly this. But actually more is true. Because you can, using the Baker-Campbell-Hausdorff formula, which tells you what is the answer. It says that for matrices, it says the exponential x, let's say x, y, z are matrices, and you take the exponential of x times the exponential y. This is the exponential of a third matrix that's called z, and z can be written as x plus y plus 1/2 the commutator of x and y. And the crucial point is plus all terms written with commutators. So you can always rewrite z as in terms of purely commutators. But then this suggests something very deep, that in a neighbor of the identity of a Lie group, you can always write an element of the group as an exponential of the Lie algebra. Can I move?
Yes, go ahead.
So there is this suggests a fact that is in fact a theorem in a neighbor of the identity of GD group. Any G which belongs to G can be written as G times equal to the exponential of some combination, let's call it's alpha, E alpha. Of course, this is itself an element of the Lie algebra. Now, like the groups, also the Lie algebras you can represent in terms of matrices acting on a vector space. Like the groups, also Lie algebras admit representation in terms of matrices or linear operators on vector spaces. And the Lie bracket is mapped into a commutator. In the case we discussed, it was already a commutator, but for any Lie group, it's always now mapped as a representation in the commutator. And so now there is a natural relation between a representation that's called D of G and a representation that's called the script of the algebra of G, which is already suggested by the relation that I gave, that G can be written near the identity, can always be written as E to some R, the A is an element of the G. And in fact, exactly what you expect. The representation of G, which can be written as E, let's say TA, you can represent as the corresponding representation of A is just obtained by taking the derivative with respect of time of T of E to the TA for T equal to 0. So you have a general G, which is exponential times T of an element of the Lie algebra. And you get a representation like this. A particularly important representation is what is called the adjoint representation. Which has the vector space in which it acts is the Lie G itself. And it is defined for the group. The adjoint representation of an element G is equal to G A G minus 1. And for Lie G, the adjoint representation of A, which is an element of G, acting on an element B, which is also belonging to Lie G, is given by the Lie bracket of A and B.
Could you move your paper upwards a little bit so we can see everything?
Sorry? Ah, okay. Sorry. I missed one. Where did I put? Okay, I have only one additional comment, which probably I left somewhere my notes, but I try to say anyway, if it's enough, what the time. Okay, I find it. So the last notion that I want to give you is that the tensor product of representation, both well, we know that besides the direct sum, we have as operation on vector spaces, the tensor product. So we can also define tensor product of representation D of G or of the Lie algebra of G. So let's suppose you have, if E1 mu is a basis of a vector space V1 and E2 nu of a vector space V2, and then, for example, the representations, and you have D1 acting on D1 and D2 acting on V2. Well, the tensor product representation D1 times D2 of, for example, of an element of the group E acting on the tensor product E mu tensor E2 nu is given by E1 rho tensor E2 sigma D1 rho mu D2 sigma nu, where we have defined dg acting on E mu, of course, can be written as a combination of the basis, which we write like dg nu mu. So this also G. Okay, maybe it's strange the position of the nu, but if you think, so you see this on this side. Why? Why do you think in terms of vectors? dg of, you remember a vector is v mu e mu. And you would like to have a representation, the contravariant vector should change like d mu nu v nu. Well, but now let's do it. dg acting on v mu is, by what we said, v mu times dg mu mu of e nu. But now change variable. Mu you change with nu. This becomes v nu dg mu nu e mu. And so you see that actually dg act on e mu by sending E mu dg mu nu. And that's it.
Sorry, can you move the page? We can't see.
Sorry, I missed that. So that's the reason why at first it looks strange, this. But if you think in terms of vectors, the contravariant vectors that we've seen in the original there was a remark in the notes, in the initial notes, that maybe a vector can also be a tensor and so on, can be a tensor with respect to the representation of a group. Here is the representation that we discussed. So this is the same if we take a similar situation I gave for a group, but you can also do for a Lie algebra of a Lie group.
I think on the bottom left-hand side, it must read E nu, right?
Sorry?
Bottom left-hand side, it should read E nu. Last line, left side.
Last line.
Left-hand side of the equation.
Okay. So the last line, it should be E
No,
nu.
no, the one below. It should read E nu on the left hand.
TG E nu should be E nu. I mix up.
Yeah, or change that.
things.
Doesn't matter.
Yeah. That should be the correct. Sorry. So that's what I've written here. But so this D nu, so E nu, okay. Okay. So I make some mix up, but if you can put it in the correct way. Yeah, so this is the one I wanted to and here I mean I wanted to, yes. So somehow this is this, and instead this one is this one. Okay, is it clear now? So okay, yes, I just made a mistake in the last. Apparently, the last formula always be I think some means. Okay, I think the only thing maybe I can add a comment. I mean, since if you have a group G, which is non-simply connected, well, and in a Lie group which is not simply connected, well, you can construct, of course, its universal covering. And now, an interesting property that the Lie algebra only knows something near the identity of the group. So certainly the near the identity is to be are equal. And so what happens is that the Lie algebra of G is equal to the Lie algebra of the covering group. Because Lie G knows only a neighbor of the identity. Okay. So actually, this is what I have prepared. So if you have questions, please. Otherwise, I've finished.
Thank you.
Okay. Do you have questions? If not, we can see each other tomorrow.
Could you motivate again why we can write group elements as exponentials of the?
Okay. I say that is a theorem. I just say that is suggested by the fact. So you mean this theorem?
Yes.
in a neighbor of the identity of a group, you can always write an element G, let's say, okay, neighbor, let's say UE of G, an element G which belongs to this neighbor can be written as the exponential of an element of the D algebra. This may be not possible for the whole group, but certainly it is possible
of the identity. Is
And,
it clear?
and why is it important that we always choose the tangent space of the identity?
The point is that I mean, if you yeah, you are in, this is a tangent space, but the exponential of something in the tangent space lives in the group. That's the point. This was in some sense suggested by the fact that if you differentiate a curve on the group, you get an element of the tangent space. But I don't claim that I have proven this. Okay, this is a theorem. It's just, to me, is this argument that, okay, I can always take a curve as e to the t a, where a is an element of the Lie algebra, looks to me natural when you take the derivative. But it's not something that I have proven. Of course, I would need many times I state something, but without proving it. It's just giving a kind of intuition what is going on, but not proving it. Okay, that's also in this case. It's not. I'm not proved this theorem.
And what is the intuition for why we consider only why we consider the tangent space for the identity specifically? What would happen if we would take another group element?
Is maybe one possibility is that let's see. Well, you can think the most simple case is just U1. Suppose you have U1, and U1 is what is the circle. Okay, locally near the identity, you can always rectify the circle. And so you get a tangent space to the identity of the identity, which is one point in the circle. And now there is a map, a bilinear map between a rectified part of the circle and a neighbor of one point of the circle. And this is the same thing that you find here. The non-trivial point is that because of the property of the group, it is not just a rectification, but it is really part of the group. You can just move through the form in such a way that it becomes really part of the group. So this is a property of the group. If your tangent space is not part of in general of the space itself, but because you have the property of the group, you can deform somehow the naive idea of a tangent space as a flat, just making it as part of the group near the identity. I don't know how to more than this.
Okay, thank you.
If there are, I mean, next lecture, unfortunately, I think it will be more mathematically sophisticated than this one. So I don't know if I will be able to cover all what I prepared. I think there it is more crucial that you stop me if you don't understand. Okay, maybe I do less, but maybe it's more useful to make it clear. Okay, so if there are no other questions, maybe Saskia, we can stop.
Yes, then let me stop the recording. Where is this?
Okay.
That is. Yes, so thank you
No, it
again.
was
Thank
fine.
you,
It is fine.
Pieralberto.
So tomorrow at the answer.
Yeah. At
1:30.
1:30 again tomorrow for the last lecture. Okay, then thanks,
Okay.
Pieralberto, and see you all tomorrow.
Bye.
Bye.
Goodbye.